For most of modern astronomy's history, cosmologists imagined the early universe as a quiet, gentle place where structure formed slowly and gradually. After the Big Bang, space expanded rapidly. Temperatures dropped from incomprehensible heat to more manageable levels, and matter spread out almost uniformly in every direction. Tiny fluctuations existed, regions that were microscopically denser than others. But gravity was expected to work slowly and patiently, requiring vast spans of time to pull matter together into organized structures. In this carefully constructed picture, the first stars were supposed to ignite reluctantly after hundreds of millions of years. Gas clouds needed time to lose energy and cool enough to collapse under their own gravity. Dark matter halos needed time to grow massive enough to trap ordinary matter. Galaxies, when they finally appeared, were expected to be small, faint, delicate structures that would require additional hundreds of millions of years to mature into anything substantial. The universe, according to this model that shaped decades of theoretical work, was supposed to learn to walk before it learned to run. Structure was supposed to emerge gradually through patient processes, not suddenly through rapid assembly. That careful expectation shaped astronomical predictions about what early universe observations should reveal. When the James Webb Space Telescope began systematically surveying the cosmos as it existed billions of years ago, astronomers anticipated scarcity. They expected to find a few primitive galaxies scattered here and there, dim objects barely clinging to existence in a young cosmos, still finding its footing, still figuring out how to organize matter into complex structures. Instead, Webb found crowds. Again and again, in survey after survey, bright galaxies appeared in cosmic epochs that were supposed to be nearly empty. These weren't faint sparks barely holding themselves together through fragile gravity. They were already busy, active systems producing stars at rates comparable to or even exceeding those observed in much later galaxies from more recent cosmic epochs. The surprise wasn't the discovery of one strange object that violated expectations. It was the pattern, the consistency, the sheer abundance of bright, massive galaxies appearing far earlier than theory predicted they should exist. Within the universe's first 500 million years, Webb detected galaxies emitting enormous amounts of light. Some contained hundreds of millions of stars worth of matter. Others appeared to contain billions of stellar masses, quantities of material that should have required far more time to accumulate than the universe had yet experienced. Gravity is undeniably powerful, but it's not instantaneous. Gas must lose thermal energy before it can collapse into dense clouds. Dark matter halos must accumulate enough mass to gravitationally trap ordinary matter. Stars themselves take millions of years to form from collapsing gas clouds, and those stars must live out their lifetimes and die before they can enrich their surroundings with heavier elements. Each step in this sequence imposes a minimum timescale that cannot be compressed indefinitely. Compress the sequence too much. Try to fit too many stages into too short a period, and the physics stops working. The processes become physically impossible. And yet, when Webb looked at the early universe, the galaxies were already there, bright and massive, as if they had somehow found a way to accelerate through stages that should have taken much longer. One of the most troubling aspects of these discoveries wasn't just the size or brightness of early galaxies. It was their chemical maturity, their elemental composition. Webb's spectroscopic measurements, which analyze the wavelengths of light to determine what elements are present in distant galaxies, revealed clear signatures of carbon, oxygen, nitrogen, and other heavy elements. These elements do not exist in meaningful quantities immediately after the Big Bang. The primordial universe consisted almost entirely of hydrogen and helium. Every heavier element must be forged inside stars through nuclear fusion, then released into space when those stars die. The presence of heavy elements in galaxies that formed just a few 100 million years after the Big Bang means something unavoidable and deeply significant. At least one earlier generation of stars must have already formed, burned through their nuclear fuel, and ended their lives, spreading heavy elements into the surrounding space. All of this occurred within the universe's first few 100 million years. The cosmic timeline was being pushed backward, compressed into a much shorter period than models allowed. To understand why this observation troubled astronomers so profoundly, it helps to think of galaxy formation as analogous to building a city. You cannot construct skyscrapers before roads exist to transport materials. You cannot pour concrete before you've produced steel for reinforcement. You cannot install electrical systems before you've generated electricity. Each stage depends fundamentally on completing the stages before it. The process has an inherent order that cannot be arbitrarily rearranged. The early universe was supposed to be laying foundations, preparing the groundwork for more complex structures that would emerge later. Instead, Webb found finished buildings standing tall, their construction somehow completed far ahead of schedule. This growing mismatch between theoretical predictions and actual observations became known among cosmologists as the impossible early galaxy problem, or the too much too soon problem. When astronomers calculated how much total light galaxies should collectively produce during the universe's first billion years based on standard models of star formation and galaxy evolution, their predictions consistently fell short of what Webb actually observed. Webb's measurements exceeded theoretical predictions by factors of 2, 5, and in some extreme cases, even 10 times the expected brightness. That magnitude of discrepancy is not a minor rounding error or a small calibration issue. It's a signal that something fundamental about our understanding is incomplete or incorrect. Scientists responded the way they always do when confronted with observations that violate established theory. They questioned everything. They questioned the measurements themselves, checking and rechecking Webb's instruments for any systematic errors or calibration problems. They reanalyzed the data using different techniques and assumptions. They investigated whether dust, which can both obscure and redirect light, might be making galaxies appear brighter than they truly are. They considered whether gravitational lensing, where massive foreground objects magnify background galaxies, could be inflating the apparent brightness of distant objects. Again and again, after exhaustive scrutiny, the results held. The early universe was not dim and tentative. It was luminous and active, filled with bright galaxies forming stars at remarkable rates. Some of these early galaxies were so massive that researchers briefly and somewhat dramatically referred to them as universe breakers, objects whose mere existence seemed to violate the fundamental limits imposed by cosmology itself. According to standard models of structure formation, galaxies of that size simply should not exist at those ages, not unless something fundamental about early cosmic evolution was seriously misunderstood. Initially, some astronomers hoped the masses were being overestimated, that something about the observations was making galaxies appear more massive than they actually were. Perhaps the light wasn't coming primarily from stars at all. Perhaps supermassive black holes at galactic centers were contributing enormous additional brightness, making galaxies appear larger and more massive than they really were, based on stellar populations alone. Further detailed analysis showed that this explanation helped partially, but didn't fully resolve the problem. Yes, some early galaxies do host extremely active supermassive black holes, whose intense radiation significantly inflates their apparent brightness. When astronomers accounted for that black hole contribution and subtracted it from total galaxy luminosity, the most extreme discrepancies were reduced. But even after making those corrections, even after removing the black hole contribution to galactic brightness, the early universe still contained roughly twice as many massive galaxies as theoretical predictions allowed. The tension eased somewhat, but emphatically did not disappear. The problem remained real and significant. This pattern repeated consistently across multiple independent surveys. Webb conducted observations in different directions, examining different regions of sky, using different instruments, and analyzing different wavelength ranges. Each time, regardless of which piece of sky was observed or which technique was employed, the result remained the same. The early universe was crowded with galaxies. Structure formed quickly. Star formation proceeded with startling, unexpected efficiency. This consistency forced astronomers to reconsider a basic assumption underlying decades of galaxy formation theory: the efficiency with which the universe converts gas into stars. In the modern universe, the one we directly observe around us, star formation is surprisingly and frustratingly inefficient. Most of the gas inside galaxies never becomes stars at all. It gets heated by radiation, stirred by turbulence, blown away by stellar winds, or disrupted by supernova explosions. A massive molecular cloud containing enough matter to form millions of stars may spend millions of years producing only a modest number of actual stars before the cloud disperses, its remaining gas blown away before it can collapse further. Only a small fraction of available gas actually ends up in stars. Early galaxies appear to have operated under fundamentally different rules, with dramatically higher efficiency. One possibility is that the early universe was simply much denser than it is today. With matter packed more tightly together everywhere, gas clouds collided more frequently, and those collisions triggered rapid gravitational collapse that converted gas to stars more efficiently than in the modern, more spread-out universe. Another idea focuses on the chemical composition of early gas. The first stars formed from nearly pure hydrogen and helium gas without any heavier elements to complicate the cooling processes that allow gas clouds to collapse. Under certain conditions, this chemically simple primordial gas may have collapsed more directly and efficiently than modern metal-rich gas that contains carbon, oxygen, and other elements affecting how gas loses energy. Galaxy mergers likely played a crucial role as well. In the early universe, when space was smaller and matter was packed more densely, galaxies were much closer together than they are today. Collisions between galaxies were far more frequent. When galaxies merge, their gas reservoirs get driven toward their centers, compressed to extreme densities that ignite intense bursts of star formation. A galaxy could potentially build much of its total stellar mass in short, violent episodes of merger-driven starburst activity rather than through slow, steady growth over billions of years. Each of these proposed explanations helps account for part of the observed pattern. None fully resolves it alone. The truth likely involves some combination of all these factors, plus others we haven't yet identified. At the centers of many of these surprisingly early galaxies lies another profound mystery. Webb has identified supermassive black holes already in place, already feeding on surrounding matter, already influencing their host galaxies when the universe was less than 500 million years old. Some of these black holes weigh millions of times the mass of our Sun. Others appear to contain billions of solar masses concentrated into regions smaller than our solar system. According to conventional black hole physics, growing black holes that massive in such a short time should be flatly impossible. Black holes typically form when massive stars dozens of times more massive than the Sun, exhaust their nuclear fuel and collapse catastrophically. The resulting black hole might weigh tens of solar masses, perhaps up to 100 solar masses in extreme cases. From there, a black hole can grow by consuming surrounding matter, but that growth rate is fundamentally limited by physics. As material falls toward a black hole, it heats up through friction and compression, eventually becoming so hot that it radiates enormous amounts of energy. That outward radiation pressure pushes back against additional material trying to fall in, creating a natural limit on how fast a black hole can grow. Even under ideal conditions, with unlimited matter available to consume, building a billion solar mass black hole through steady accretion should require far longer than the 500 million years the early universe had experienced. The math simply doesn't work. Yet Webb keeps finding them, massive black holes that somehow already exist in an era when they shouldn't be possible yet. This persistent observation has forced astronomers to seriously consider formation scenarios that once seemed too extreme or speculative to take seriously. Perhaps some black holes formed through direct collapse of massive primordial gas clouds, skipping the stellar stage entirely and creating black holes weighing thousands or tens of thousands of solar masses right from the start. Perhaps the very first generation of stars, the so-called population 3 stars that formed from pure hydrogen and helium, grew thousands of times more massive than any modern star, collapsing directly into very large black holes when they died. Perhaps black hole mergers, violent collisions where two black holes spiral together and combine into one larger black hole, were far more common in the dense early universe than current models assume. None of these ideas has been conclusively confirmed. None can yet be ruled out. The observations demand explanations that push theoretical boundaries. What makes this early period so critically important is that these rapidly forming galaxies and impossibly large black holes shaped absolutely everything that followed in cosmic history. Their intense radiation transformed the universe during an epoch known as reionization, stripping electrons from hydrogen atoms throughout space and making the universe transparent to visible light for the first time. Their supernovae explosions enriched intergalactic space with heavy elements, seeding future generations of stars and galaxies with the chemical ingredients needed to form planets and eventually life. Their gravity pulled surrounding matter into the first large-scale structures, the earliest filaments and clusters that would eventually grow into the vast cosmic web we observe today. If these structures formed earlier and more efficiently than standard models predicted, then the entire timeline of cosmic evolution must shift. Everything we thought we understood about when various stages of structure formation occurred needs revision. And as Webb continues looking deeper into cosmic history, pushing closer to the absolute limits of observable distance, the pattern becomes increasingly difficult to ignore or dismiss. The universe did not wait patiently for billions of years to become complex and organized. It rushed forward, assembling stars, galaxies, and black holes at a pace that genuinely challenges our most carefully developed equations and models, which leads to an unavoidable realization with profound implications. If the universe could build this much sophisticated structure so incredibly quickly during its youth, then the true scale of what exists today, after 13.8 billion years of additional growth, evolution, and structure formation, may be vastly larger than humanity ever imagined. And that realization becomes impossible to escape when Webb does something even more fundamentally unsettling than revealing early galaxies. It systematically counts how many galaxies actually exist throughout the observable universe, and the numbers it returns challenge everything astronomers previously believed about cosmic census taking. For most of the 20th century and into the early 21st, astronomers believed they had reached a reasonable, defensible answer to one of the most fundamental questions imaginable. How many galaxies exist in the universe? The methodology was conceptually straightforward, even if technically challenging and time-consuming in practice. Point the most powerful telescope available at a tiny, seemingly empty patch of sky. Expose the telescope's detectors for many hours, collecting every photon possible. Count every galaxy visible in that deep image. Then scale that number upward to cover the entire observable sky, accounting for the full sphere of direction surrounding Earth. When the Hubble Space Telescope performed its deepest observations in the mid-90s and early 2000s, producing images known as the Hubble Deep Field and later the Hubble Ultra Deep Field, it revealed nearly 10,000 galaxies in a region of sky no larger than a grain of sand held at arm's length, or about 1/13 millionth of the total sky area. That image shocked the astronomical community and captured public imagination worldwide. From those observations, astronomers carefully estimated that the observable universe contained somewhere between 100 billion and 200 billion galaxies total. The number was almost psychologically impossible to comprehend. 200 billion separate galaxies, each containing billions or hundreds of billions of stars, each potentially containing billions or trillions of planets. And for years, through the 2000s and into the 2010s, that estimate stood as humanity's best answer. 200 billion galaxies filling the observable universe, an incomprehensibly vast number that nonetheless felt like progress, like humanity had finally measured something fundamental about cosmic structure. Then the James Webb Space Telescope turned its gold-coated mirrors toward the same regions of apparent darkness that Hubble had surveyed, and everything changed again. Where Hubble saw black gaps between visible galaxies, dark spaces that appeared empty of structure, Webb detected faint infrared glows, marking additional galaxies that had been invisible to Hubble's instruments. Where Hubble had captured smudges barely rising above instrumental noise, unclear blobs that might or might not be distant galaxies, Webb resolved clear galactic structure. Regions that once felt empty suddenly revealed themselves as crowded, layered with multiple galaxies at different distances, alive with distant systems that had remained completely invisible to previous observations. This difference wasn't a failure or limitation of Hubble. The Hubble Space Telescope performed magnificently for over 3 decades, revolutionizing astronomy and delivering discoveries that reshaped our cosmic perspective. But Hubble was fundamentally limited by wavelength, by the portions of the electromagnetic spectrum its instruments could detect. As the universe expands, light from distant galaxies gets stretched into longer wavelengths through the redshift effect discussed earlier. By the time light from the most distant galaxies reaches Earth, it no longer exists in the visible wavelength range that Hubble was primarily designed to observe. The light has shifted into infrared wavelengths, becoming invisible to Hubble's cameras but perfectly detectable to Webb's infrared-optimized instruments. The galaxies were always there, scattered through space, their light traveling toward Earth across billions of years. That light had simply slipped past our observational capabilities, existing in wavelengths we couldn't yet detect. Webb was specifically designed and built to catch it. In one of Webb's most ambitious and technically demanding observation programs, astronomers surveyed a region of sky only slightly larger than 3 full moons placed side by side, a tiny patch representing roughly 1,000th of the total sky area visible from space. For hundreds of hours spread across multiple observing sessions, Webb collected more than 10,000 individual exposures, each one capturing faint infrared signals that had traveled across billions of light years of expanding space. When those thousands of exposures were carefully combined, aligned, and processed, removing noise and artifacts while preserving real galactic signals, the result was genuinely staggering. Nearly 800,000 distinct galaxies filled the frame. 800,000 separate galaxies visible in a patch of sky most people would glance at and dismiss as empty darkness. To truly grasp the scale of that result, imagine printing Hubble's famous ultra-deep field image on a standard sheet of paper, the kind you'd use in a home printer. To display Webb's deep field image at the same level of detail, at the same scale, showing the same amount of sky, the print would need to be more than 13 feet tall and 13 feet wide. A wall-sized mural of cosmic history, and every single point of light in that enormous mural is not a star but an entire galaxy. Each of those 800,000 galaxies contains anywhere from millions to trillions of individual stars. Many host complex planetary systems orbiting those stars. Many contain rich chemistry, clouds of dust and gas enriched with heavy elements forged by generations of stars that lived and died. Some harbor active supermassive black holes at their centers. Some are actively forming new stars. Others have exhausted their gas and fallen quiet. The universe, it turns out, is not sparsely populated with isolated islands of matter drifting through vast emptiness. It's densely packed at every scale, layered with structure everywhere we look, crowded with galaxies extending to the very limits of detection and undoubtedly continuing beyond. For generations, humanity looked up at the night sky and believed we understood the boundaries of existence. The universe, scientists concluded, stretched approximately 14 billion light-years in every direction from Earth. Within that incomprehensible volume floated a few hundred billion galaxies, each containing billions of stars, all scattered through the darkness of space like islands in an endless ocean. The numbers were staggering, almost beyond comprehension, yet they felt manageable. They felt finite. They felt like something we could eventually catalog, measure, and fully understand. Then, humanity pointed the James Webb Space Telescope toward regions of space that appeared completely empty to every instrument we had ever built before. And everything we thought we knew shattered like glass. Webb didn't just reveal a universe slightly larger than expected. It unveiled an observable cosmos stretching 93 billion light-years from edge to edge, absolutely teeming with galaxies that had been hiding in wavelengths of light our eyes and previous telescopes simply couldn't detect. It discovered fully mature galaxies existing just 300 million years after the Big Bang, timeframes so impossibly early that their existence challenges the fundamental physics we use to describe cosmic evolution. It found supermassive black holes that grew to impossible sizes in impossibly short periods, defying every model of how these cosmic monsters should form and develop. But perhaps the most profoundly unsettling discovery Webb has delivered isn't about how far it can see into the cosmos, or even about the ancient structures it has revealed in the earliest epochs of universal history. The truly earth-shattering implication is what all these observations tell us about what exists beyond the absolute limits of observation itself, and why the overwhelming majority of reality may be permanently, fundamentally, forever beyond our reach. To truly grasp what the James Webb Space Telescope has revealed about the universe, we must first abandon one of the most deeply ingrained assumptions about how we perceive reality. We instinctively believe that when we look at something, we're seeing it as it exists in that moment. Your brain processes the world around you as if everything is happening simultaneously, as if the present moment is a universal constant shared by everything in existence. That comfortable illusion works perfectly well in daily life, but it represents a fundamental misunderstanding of how reality actually operates. In truth, there is no universal now. There is no cosmic present tense. Everything you perceive is already history by the time you experience it. This isn't philosophical abstraction. It's the inevitable consequence of a simple fact. Information cannot travel instantaneously. Light, electromagnetic radiation, Every signal carrying information from one point to another moves at a finite speed. That speed is extraordinarily fast, approximately 186,000 miles every second. Fast enough to circle the entire Earth more than 7 times between one heartbeat and the next. Nothing in the universe moves faster. Nothing can move faster. This represents an absolute speed limit built into the structure of reality itself. Yet even at that incomprehensible velocity, distance transforms instantly into delay. The farther light must travel to reach your eyes, the older the image it carries when it finally arrives. Every observation becomes a glimpse into the past, with the depth of that past determined entirely by how far the light has traveled. Consider what this means in practical terms. When you see a building 1 mile distant, you're actually observing it as it existed roughly 5 millionths of a second ago. The light reflecting off that structure took that tiny fraction of time to cross the space between the building and your retina. You're not seeing the building as it exists now. You're seeing a recording of how it appeared 5 millionths of a second in the past. The delay is so infinitesimally small that it makes no practical difference, but the principle remains absolute. Now extend that principle outward. When you look at the moon hanging in the night sky, you see it not as it exists in your present moment, but as it appeared 1.3 seconds ago. That's how long it takes light to cross the 240,000 miles separating Earth from its natural satellite. If the moon were somehow to vanish in an instant, you would continue seeing it hanging peacefully in the sky for another second and a third before the information about its disappearance could possibly reach you. The Sun, sitting at the center of our solar system 93 million miles away, appears to us as it existed 8 minutes and 20 seconds in the past. Every sunrise you've ever witnessed, every sunset you've ever watched, every moment you've spent basking in sunlight happened 8 minutes after the light carrying that warmth left the sun's surface. We don't see the sun as it is. We see it as it was, perpetually watching a broadcast delayed by the time it takes light to cross the solar system. The night sky, that vast canopy of stars we've gazed upon throughout all of human history, is not a live feed of the cosmos. It's an archive of information, a museum of light carrying messages from countless different moments in time. Every star visible to the naked eye exists in our own Milky Way galaxy. Yet even these relatively nearby neighbors appear to us as they existed years, decades, or centuries in the past. Proxima Centauri, the nearest star beyond our Sun, sits 4.2 light-years away. When you see its faint light, you're observing it as it appeared 4.2 years ago. The light you detect tonight left that star's surface over 4 years in the past, traveling through the emptiness between stars while entire seasons cycled through on Earth, while your life changed in countless ways, while history unfolded in complete ignorance of that ancient photon's patient journey toward your eye. The center of our Milky Way galaxy, that dense core where hundreds of billions of stars orbit a supermassive black hole, exists 26,000 light-years from Earth. Every image we capture of the galactic center shows it as it appeared 26,000 years ago. When those photons began their journey, humans were still living in the Stone Age, struggling to survive in a world we would barely recognize. The entire span of recorded human civilization, every empire that has risen and fallen, every great achievement and terrible tragedy, all of it occurred while those photons traveled silently through space, carrying their ancient message forward through time. As our observations reach beyond the Milky Way into the incomprehensible spaces between galaxies, we stop observing anything resembling the present. We become witnesses to earlier and earlier chapters of a story that has been unfolding for billions of years. The Andromeda Galaxy, our nearest large galactic neighbor, appears to us as it existed 2.5 million years ago. Other galaxies in our local group show themselves as they were tens of millions of years in the past. The night sky transforms from a simple display of distant lights into something far more profound, a temporal archive where every point of light represents a different moment in cosmic history. The closer objects appear nearly contemporary. The farther objects reveal progressively older versions of reality. Every photon becomes a time capsule, a messenger carrying information about when and where it was created, preserved perfectly during its journey across the universe. But the universe does not preserve these messages in their original form. As space itself expands, something remarkable and fundamental happens to every photon traveling through it. The expansion of space stretches the light itself. Imagine a wave traveling across the surface of an ocean. The wavelength, The distance from one wave crest to the next determines many of the wave's properties. Now imagine that ocean suddenly growing larger, with every point on its surface moving away from every other point. As the ocean expands, the wave gets stretched along with it. The distance between crests increases. The wavelength grows longer. Light behaves exactly the same way as it travels through expanding space. When a photon is created, it has a specific wavelength determined by how it was generated. High-energy photons have short wavelengths, appearing blue or ultraviolet. Lower-energy photons have longer wavelengths, appearing red or infrared. But as space expands during the photon's journey, the wavelength gets stretched. That energetic blue light gradually shifts toward red. That ultraviolet light moves into the visible spectrum, then continues shifting into infrared. This phenomenon, called redshift, isn't merely a cosmetic change in color. It's a precise record of cosmic expansion, a measurement of how much the universe has grown since the photon began its journey. The more stretched the light, the longer it has been traveling, and the earlier in universal history it must have been emitted. Redshift acts as a cosmic timestamp, allowing astronomers to determine not just how far away an object is, but when in the history of the universe it existed. The most distant objects visible in the sky don't just appear far away, they appear ancient. Their light stretched by billions of years of cosmic expansion, carrying information about an era when the universe was fundamentally different than it is today. For most of the 20th century, astronomers relied heavily on telescopes optimized to detect visible light and ultraviolet radiation, the narrow slice of the electromagnetic spectrum that human vision evolved to perceive. These instruments revolutionized our understanding of the nearby universe. The Hubble Space Telescope, launched in 1990 and operating for over 3 decades, transformed humanity's view of galaxies, nebulae, star-forming regions, and the large-scale architecture of cosmic structure. But as scientists attempted to peer farther back in time, to observe the universe as it existed in its earliest epochs, something frustrating began to happen. The universe seemed to fade away, not because nothing existed in those ancient eras, but because the light from those distant objects had been stretched so dramatically by billions of years of cosmic expansion that it no longer appeared in wavelengths Hubble could detect. Those ancient galaxies didn't disappear. Their light simply drifted beyond the range of visible and ultraviolet observation, slipping into the infrared portion of the spectrum where Hubble's instruments struggled to function effectively. It was as if humanity had been trying to listen to a conversation happening in a frequency range our ears couldn't detect. The information existed, traveling through space toward us, but we lacked the proper tools to receive it. The James Webb Space Telescope was specifically designed to solve this problem, to follow that missing light wherever it had gone. Webb's primary mirror spans more than 21 feet in diameter and consists of 18 hexagonal segments, each coated with a microscopically thin layer of gold, precisely 99 nanometers thick. Gold was chosen for a specific reason. It reflects infrared light with exceptional efficiency, far better than the aluminum coating used on most optical telescopes. Webb doesn't orbit Earth like Hubble does. Instead, it operates at Lagrange Point 2, a gravitationally stable location nearly 1 million miles from Earth, roughly 4 times farther than the Moon. This remote position offers crucial advantages. Webb sits in permanent shadow, shielded from the heat and glare of the Sun, Earth, and Moon by a tennis court-sized sun shield consisting of 5 layers of specially designed material. That thermal isolation is absolutely essential because Webb is an infrared telescope, and infrared radiation is intimately connected with heat. Everything warm emits infrared light. A telescope operating at room temperature would generate so much infrared radiation from its own structure that it would completely overwhelm the faint signals from distant galaxies. To detect ancient light that has been traveling for billions of years, Webb must become incredibly cold, operating at temperatures barely above absolute zero. Webb's instruments are cooled to approximately minus 370 degrees Fahrenheit, cold enough that the telescope itself generates almost no infrared radiation. Only at these extreme temperatures can Webb become sensitive enough to detect the faintest whispers of ancient light, photons that have been stretched and diluted by their journey across almost the entire observable universe. When Webb stares at a patch of sky that appears utterly black to human eyes, to Hubble, to every ground-based telescope, it isn't searching for emptiness. It's waiting with mechanical patience, collecting photons one by one as they arrive after journeys lasting billions of years. Webb might observe the same tiny region of sky for dozens of hours, even multiple days, patiently gathering every photon it can detect, building up an image from light so faint that each individual photon matters. And what Webb finds in that apparent darkness is not a tentative, primitive cosmos just beginning to organize itself. It finds a universe that is already surprisingly mature, already busy with activity, already filled with structure. Some of the galaxies Webb has detected formed when the universe was merely 300 million years old, less than 3% of its current age of 13.8 billion years. To put this in perspective, imagine compressing the entire history of the universe into a single calendar year. In this analogy, the Big Bang would occur at the first moment of January 1st. These incredibly early galaxies would appear on January 2nd, just one day after the universe itself began. According to the cosmological models that astronomers spent decades developing and refining, this epoch, often called the cosmic dawn, should have been a relatively dim and quiet period. The universe had just emerged from what's known as the Dark Ages, a period when space was filled with neutral hydrogen gas that blocked almost all light. The very first stars were expected to ignite slowly and tentatively. Early galaxies were predicted to be small, fragile collections of gas and newborn stars, requiring hundreds of millions of years to accumulate enough matter to become bright and substantial. But Webb saw something completely different. It discovered galaxies that were already bright, already massive, already forming stars at intense rates that rival or even exceed the star formation activity in much later galaxies. Some were luminous enough that even if they were significantly more distant than initial measurements suggested, Webb could still detect them easily. That brightness carries profound implications. Bright galaxies require vast populations of stars, and stars do far more than simply shine. Inside their cores, nuclear fusion forges heavier elements that didn't exist in the universe's earliest moments. The Big Bang produced primarily hydrogen and helium, with trace amounts of lithium. Everything heavier than those primordial elements, every atom of carbon, oxygen, nitrogen, iron, and all the other elements that make up planets and life itself, must be created inside stars through fusion. Those heavier elements only escape into space when stars die, either through stellar winds during their lifetimes or through explosive supernovae at the end of their existence. When Webb detects significant quantities of heavy elements in galaxies that form just a few 100 million years after the Big Bang, it's seeing irrefutable evidence that earlier generations of stars must have already completed their entire life cycles. This means the universe had already gone through multiple cycles of star formation, stellar evolution, and stellar death far sooner than our models predicted. Stars had formed, lived their lives, and died, enriching the interstellar medium with heavy elements, all within the universe's first few 100 million years. The cosmic clock wasn't just running on schedule, it was running fast, accelerating through stages of complexity that were supposed to take much longer. The universe didn't slowly ease into complexity through gradual processes unfolding over vast timescales. Instead, it rushed toward organization and structure with surprising urgency. This discovery fundamentally challenges our understanding of how quickly matter can organize itself under gravity's influence. There's also something profoundly humbling about the nature of these observations. Webb doesn't capture these images instantaneously like a camera photographing something in the same room. It gathers photons that have been traveling for more than 13 billion years, particles of light that began their journey when the universe was young, unfamiliar, and drastically different from the cosmos we inhabit today. When that ancient light started moving through space, Earth did not exist. The sun had not formed. The Milky Way was still assembling itself from clouds of gas and dark matter that would take billions of years to coalesce into a mature galaxy. There were no planets, no oceans, no life, no observers to witness those distant galaxies in their youth. Every chapter of Earth's history, from its formation through its entire geological timeline, every species that has ever lived, every civilization that has ever existed, the entire span of human experience from prehistory to the present moment, all of it unfolded while those photons were already traveling through space, carrying their message forward through time. By the time Webb finally detects them, we're not witnessing current events. We're not seeing these galaxies as they exist today. We're witnessing moments that happened once, impossibly long ago, preserved perfectly in transit like messages in bottles cast across an ocean of space and time. never to be repeated in quite the same way. This is why astronomers say the James Webb Space Telescope doesn't simply look far away into distant regions of space. It looks backward through time itself. Distance and time become inseparable concepts. Nearby objects reveal the universe closer to the present. More distant objects show progressively earlier stages of cosmic history, like turning back the pages of a book until you reach chapters written billions of years ago. Yet even Webb's extraordinary capabilities, even its unprecedented sensitivity to infrared light, even its position at Lagrange point 2 shielded from interfering radiation, cannot overcome a fundamental limit imposed by physics itself. No telescope, regardless of how powerful humanity might eventually build it, can see beyond a boundary determined by the nature of cosmic expansion and the finite age of the universe. That boundary is called the observable universe, a vast sphere centered on Earth with a radius of approximately 46.5 billion light-years in all directions. Webb is now pushing observations closer to that absolute boundary than any previous instrument, detecting galaxies at distances once thought completely unreachable, revealing structure in epochs so ancient that light from those eras has been traveling for nearly the entire history of the cosmos. But even Webb, with all its technological sophistication, cannot observe beyond the cosmic horizon. And this is where our understanding of reality becomes genuinely unsettling, where the implications of cosmic expansion begin to reshape how we must think about existence itself. Space does not stop at the edge of what we can observe. The universe doesn't end at the cosmic horizon like continents ending at the ocean shore. Beyond that observational boundary, galaxies continue to exist. Stars continue to ignite and burn through their fuel. Black holes continue to merge in violent collisions. Planets continue to form and orbit their suns. Entire cosmic histories continue to unfold in regions that are forever hidden from us, not because our technology is inadequate, not because we lack sufficiently powerful telescopes, but because the fundamental structure of spacetime itself prevents information from those regions from ever reaching us. The James Webb Space Telescope has not only shown us how far our observational capabilities can reach, it has simultaneously revealed how much of the universe lies permanently, fundamentally, beyond any possible observation. As we absorb what Webb has discovered within our observable bubble of reality, the early brightness of ancient galaxies, the rapid formation of complex structures, the sheer abundance of galaxies filling apparently empty space, a more profound question inevitably emerges. If this much exists in the relatively small fraction of the universe we can see, what does that imply about the true scale of everything that exists beyond our view?